have some open discussion. There's not a real hard and fast way we have to run this today, but I just do want to bring up the unforeseen issues that you can find in electric motors and pumping and applications that really can't always be measured because they happen so fast, and also that they're not normally even brought up by several of the manufacturers and people in the industry. People don't want to talk about some of the negatives of things, and I don't either like go negative, but I do like to bring up what I've seen in the industry. I'd also like to invite you today. I started this group. It's called Nikola Tesla's Today's Solutions and Collaborations. It's a group of roughly about 2,500 people worldwide that are all working to advance a lot of what Nikola Tesla was originally the one that developed the first induction motor on AC. And I do have a copy of his, I call it his fundamental Bible over here, that was written in like 1907 or something like that. But in there, he talks a lot about a lot of technologies. He was obviously way ahead of his time in his view of applications of what was going on. His mind worked, quite interestingly. He developed a lot of things that kind of an unsung hero that I followed a lot in my career, and I found to give me a lot of inspiration. One thing I also like to bring up is at the beginning of every class, I've done a lot of work with the power companies, and it's very important to always, bring back up about, risk of electrical shock and death. Electrical power is something that is, you don't see it. So, a lot of people open a panel that don't, follow some of the rules, and, that's when, people get hurt. And especially in the type of power that this is dealing in, I deal in powers that are, some lower voltage in the 24-volt range, but also a lot of 480 volt, 4160 volt, 2300, very high voltages that there's just a lot of safety precautions that you have to be aware of. So I just like to bring it up. It's a thing that give me a little background on myself. Some of you probably know me. I think I've got some people that are repeating back and forth. My father started William Fritz in 1953, our original parent company. And he was putting up wind chargers. And from that, then he went on to build several manufacturing companies, some rebuilding motor remanufacturing companies that still exist in the Midwest. I'm very grateful to have him as a father. We're moving on to our fourth generation over here already. This is my grandson. I'm on the far right. He's in one of our panel facilities in the Midwest, where they build a lot of specialized panels for the aggregate industry, irrigation, multiple things, and special panels for some of the steel industry. And so, I'm proud to have my, grandson to follow along. My let's see, a little bit more on myself is I've spent about 40 years working alongside also utility companies, PG&E, Southern California Edison, National Grid, Eversource, of doing a lot of pilot studies on original implementation of variable frequency drive technologies. And from that, it's given me kind of a wealth of knowledge of what they're looking at. Also what is providing, true savings and true opportunities in the industries. I've also worked very heavily back in the 90s with EPRI, Electrical Power Research Institute. I've spearheaded a project in 1995 that they evaluated multiple locations of drive applications on injection molding machines for energy conservation. And from that, it also gave me a lot of wealth of information of what the EPRI, and a lot of people may or may not know who they are, but they're the group that actually does a lot of oversight work to review technologies, and they were doing ASDs, which are basically also adjustable speed drives, variable frequency drive, and it did prove out to be a quite a substantial savings. There's two patents that I think are important to be aware of that were the United States is they're both by this fellow named Nolan. One was in the 80s, which was the variable frequency drive, who developed, for NASA, the original, PWM type drives. And then from that, it's kind of interesting, the rest of the world kind of followed suit in some of that. And then he also built a Thyristor drive, which was designed for, which is used today. A lot of people call them as soft starts, but there's also ways that those can be utilized to save energy. And I'll get into that a little bit further, as we go on here. But it is these two important patents, one in the 80s and one in the 70s, that were both by this Frank J. Nolan, a very brilliant guy, did a lot of work for NASA.
When you think of electricity, you think of Edison. But there is one electrical genius who is nearly forgotten. A man who dreamed of giving the world an unlimited supply of energy. His name was Nikola Tesla. This is the story of a modern Prometheus who changed the world with electricity. It was Nikola Tesla who captured the power of Niagara Falls with his alternating current system and made it possible to transmit electricity to all of America and the world. Suddenly knew he could recreate this rotating field by powering the coils of a motor in different steps or phases, like the pistons of an engine. The resulting forces of magnetic attraction and repulsion would literally twist the rotor in a circle, the electrical equivalent of the wheel. And all this was accomplished with alternating currents. It would soon turn the wheels of industry around the world. Tesla was ready to unveil his motor to the world.
The subject which I now have the pleasure of bringing to your notice is a novel motor which I am confident will at once establish the superior adaptability of alternating currents.
So here we are now, in 2022. He did that in the 1870s, I believe it was, when he first started building the induction motor. But it's still the very similar principles. And that's one thing that my dad had taught me very young, is to keep it simple. Really get down to the fundamentals of what's exactly happening. And so, everybody deals with it every day, is this alternating current. We have it in our outlets in our house, we have it in our, stoves, refrigerators, or whatever. And we have all of these, rotating induction motors that drive industry. Roughly about 70% of the world's power goes into electric motors. And it's an area where there's been a lot of study, a lot of hope that we can, do it more efficiently. But in reality, the induction motor is a pretty efficient device, especially in the three-phase. They're up in the 90s now, 93, 94% efficiency. So it isn't so much the motor itself always, it's actually the application of the motor to its given pump, its given fan, its given item, is that it's one, matched with its magnetism, and also that it's matched, to its speed, to its actual required, amount of flow, pressure, in the industry. So I'm just going to go through real quickly. Most of these motors, yet today, roughly 20 horsepower and below, are just started with, this is just a simple diagram of a magnetic starter. And so everybody sees that these are just a set of, contacts that close, just turns the power onto the motor. The issue is the difficulty is this, that because the 60 cycle power, and if you, let's say it's a 480 volt source or 240 volt source, the motor, because it's not up to speed, when this motor starts turning, before that rotor starts turning, it's just a resistance here. So that current that can flow, when you just turn it on straight with a set of contacts, can be anywhere between 3 to 6 times the value. So let's say you have a 100 amp motor, it can take 500 amps to start it. So that then drives your requirement for generators, power lines, transformers, everything else. So from that point, they went on and they created part winding. So they would shift in just half of the winding here with 1, 2, and 3. And then after it got up to speed with the time delay, they would bring in the other half of the winding. This is still, done quite a bit with contactors, but it's a way of also, starting that motor. They also do a connection for a Y delta, where they connect it in a Y delta application similar here, to where you can connect the motor out and put 277 volts across the, what you'll normally be line to line after you go through your configuration of starter. And what ends up happening is that will give pretty good torque because you've got all the windings involved. Plus it will, so there's many applications you can do the either the part winding or the Y delta and just do it with contactors. And it drops the starting current from, let's say it was 500, drops down to maybe 250, 175, to start it, which it helps. From that point, then they developed the soft starter, and this is that patent that Nolan created. And these are basically thyristors here, and instead of having all the combinations of starters and contactors and time delay relays and all this stuff, they're basically able to trim the actual power. So when the motor came on here, they would turn these thyristors on and off, and you'll see more of a pulse train here. So here's the original voltage waveform. Then they started, turning it on just a small amount. You can see that they just further and further, they were switching on and off these in the positive and negative. And so it started giving this kind of a pulse voltage form. Well, that in turn gave us a lot of control over that sine wave, again, to reduce the amount of inrush current. And then Nolan had taken it even further, where they have, went to a point where they've brought the motor, back. This is a little video of this has 7 parameter wizards where you basically just select the motor, and this is the soft start. So you're able to, like a conveyor, which needs more torque, or compressor, fan, pump, whatever it is, that you can select from the manual what you want to do with it. You're also able to then set in the motor parameters, which I'll do in a second. So we select the submersible pump there. And then you just simply go ahead and set the motor amperage of the motor. High starting torque, low starting torque. As you're selecting, going through most water pump applications. So that allows us to go through that, and then we'll see here. And then just function against the loaded application. this is still in the mode of the thyristor. So this is actually compensating the current to the motor. So you can leave it into this state, into automatic compensation, and look at the total power that it's drawing. And then when it kicks over, it'll actually give you the full sine wave back. But the benefit of this is it does give you added savings. And that's what Nolan was originally pushing, is the savings. The issue is that you have to size the soft starter or the thyristor device to be able to handle that continuous current, not just a set of inrush, startups. So some of the industry has gotten to where they've, provided a little bit weaker soft starter to get by, to compete with competition. But at the end of the day, you want a heavy thyristors in there that can actually keep that current and handle that current continuously, because this can give you as much as an extra 10 or 15% on your pump of how much total power it is, especially if you're regulating and throttling the valve or the output. Now you're getting all that. Go on. I'm also been involved with ESA for many, many years. My father was a past chapter president and a director. This group is out of St. Louis, Missouri. There's actually a convention coming up the end of June. I will be attending and also be there. But this started in 1944, and it's a group of electrical people. Some of you may be on this call, maybe part of ESA, or even have you're maybe certified or been involved in there. There's in the United States roughly about 3,000 companies. Worldwide, there's about 5,000 to 6,000 companies that all follow these ESA standards. And they have this little electrical pocket handy book. The thing, I think, is like 15, 20 bucks or whatever. You can go online and get it from them. But inside here has a wealth of information. And this is one area that I want to start with about motor failure and why they're happening. One of the big areas is that the motors today are designed a lot closer to tolerance of total load, because then your power factor is better, your motors. But that's ideal application. And when you get out into a pumping world, and you have various transformers, you have Y or delta type power sources, open delta. What happened is those three legs feeding to the motor are not always balanced. And so this gives you the actual best deration factor, so you can maintain the life of those motors. And so you can see on the right hand side here is that when it's balanced, maybe a 1% deviation, you don't have to derate the motor. But when you get out to 5% of voltage imbalance, you're supposed to be derating that motor by 25% in order to maintain its life. So that's where a lot of motor people get into trouble, is because it looks good. The power, is up to 460 volts, and the power comes and says, well, we balance you to, plus or minus 10%. But it's the balance of those three waveforms. So if you've got three waveforms feeding out to the motor here, A, B, C, and you have a voltage drop between here and here, maybe it's like 440 volts, and this is 460 volts, and then between 1 and 3 it's 470 volts. Well, you need to calculate those imbalances and determine where you should be on this curve of deration of the motor. It also has here, motor performance. What happens to torque, the amperage, when you get off of its, variations of voltage. So if you're at 0, meaning that they're all balanced, or when you start, getting off 5, 10%, you can see here quick what happens to the full load amps, what happens to the power factor, the starting amps, torque ability. So this is a good point to start with if you're having troubles, to determine, where are you on the curve, because they were all designed, especially the later motors that are out today, they were all designed for, optimal application. Well, we're not in optimal application. And then well, you don't want to oversize it too much, and you definitely can't undersize it. So just a big point that I really bring up about voltage and balance. The other area then is the actual horsepower and power draw. A lot of energy conservation has been considered about the affinity law, so that when you slow a motor down like 10%, that the actual horsepower drops by the cube. And so, yes, it's fine, but you also have to look at, the amount of flow for your total CFM that you're providing for the item. So there's a lot of drive controls, and I talk about VFDs where they're changing the frequency to the motor and the voltage to the motor, but you got to look at the total volume, of liquid to get into the tank, total volume of acre feet of water provided to the irrigation site. So, don't be fooled that, yeah, it looks like it appears it's drawing less, but it may take you, that much more in time, of that pump running. So your average, power utilized will tend to be almost the same. And so what I really look at is what is your optimal efficiency of the system. So a lot of you on here are probably pump people or have experience with that, is that, every pump, its impeller, its speed it's designed for, its test point, have its best efficiency point of the pump. And that's, typically at this point on the curve. They give you a range, this is the best range to run in between here and here on the curve, on your efficiency. And then this is, better. And then this is, good or satisfactory. But you have to look at what is the actual efficiency going to. So there's a piece of software that's available by a fellow out of Australia with the Water Pumping Institute that I had to recommend if you're doing VFD control. And I'm going to go into a little bit how the VFD works in a couple of minutes here. But this allows you to plug in, because the pump companies normally will give you one curve for 1800 RPM. They don't show you that this best efficiency point does not slide linearly as you adjust the speed. So, a lot of people think, oh, well, it's just up and down, I'm slowing it down. Well, no, that's not necessarily capable, because that impeller may not pull as much water as it did before. And this curve, best efficiency point. So this tool allows you to plug in, 3 different speed ratings where you're going to be running that pump, your lower efficiency and your maximum efficiency. Maximum frequency, same efficiency frequency. Plug that in, and it'll plot where the curves will be, and it'll find out where that best efficiency point is. Very helpful tool. Rob has like 40 years in the pumping industry. Excellent, smart guy. Worked a lot with the large pumping systems, and then went in more independently in the industry. Again, getting back to that proper pump curve, especially today with less and less water available in our irrigation systems, where the water level is, this efficiency and amount of head that you've got to lift. So let's say I know some friends of mine over in Madeira area, their water level drops as much as 40 and 50 feet between the beginning of an irrigation season to the the end and the middle, or even on weekends when everybody else is pumping, it's also bringing that. Well, that's all in how far you've got to lift that water from the ground and bring it up. And so again, that slides where are we at for best efficiency point. And sometimes it's not known, and then you go add a new filter in the system, or you put a new set of sprinkler heads and changing the head pressure. You've got a filter in there that may be dropping 10 or 15 pounds across the pump. Again, that affects the total efficiency of the system. So that's one thing that's also important about, Rob also has a lot of information about that. It's not just the cube law, the affinity law of savings. It's the efficiency of every item. So that's why now a lot of the new, like center pivot irrigations and those are all designed to go low pressure, because that means that they can still, get the water out of the pipe and, feed it to the irrigation system, but they're doing it at a lower pressure. Well, all those pressures all control where is the efficiency of the total head, in that pump system. But again, go get back to the pump that you have to make sure that that's running at that sweet spot, of the application. Because I want to go in just a little bit further now into the VFD side of this. Is so there's a lot of variable frequency drives out there that are in the marketplace. They have become much more efficient. And what they're talking about is the efficiency of the transistors. They're getting better and better all the time. But there is a cost of power to transfer this. So you can see this is an original diagram of what's happening is that on a variable frequency drive, we're first converting that three-phase power to DC. So we're creating DC power in here. And like on 480 volt circuit, this would be about 700 volts DC, 700 to 800 volts, depends on how much input voltage you got. So people understand a little bit. This is a link choke. You'll hear that a lot in the circuit. Some people don't put link chokes in. They put 3 coils out here, and they put what they call line reactors. And what that is to do is to, and I'll show you in a minute how that affects it. And then this is the transistor firing out, and we're rebuilding what they call PWM. About 95% of the VFDs today are PWM, pulse width modulated. But this does have losses in it. You get losses in your inductors, there'll be line reactors, get losses in your diodes, you get losses in here. So this in average can anywhere be about 3%, of the total power. And then you put this, could be another 2 or 3% here, and then they put another line reactor on the output, and then you got another 2-3%. So all of a sudden you may have 5 or 6% loss. So that doesn't change anything as far as the total power. So if you go back and you design your pump to operate at your best efficiency point, and you can use back to what I was showing you originally on the soft starter, the only losses in here are the thyristors. And then once they're up and running, this contactor bypasses. So you literally eliminated that 5 or 6% loss here, that happens with a VFD. But it does require, more calculations and design to get that to the optimal efficiency point. So you maybe do not need a variable speed drive, and just use it for soft starting to soft start the water hammer, both up and down in speed. You can do that with a soft starter. And again, you basically have your diode front end. You have your DC bus filter, which is coming off here. So that's measuring this here. You can see that the diodes just invert the blips of the sine wave we were talking about earlier and put them all one direction, feed them into capacitors to give you a filtering voltage, because we want this as clean and smooth as possible. So as we go into these firing transistors that are feeding the PWM, that's a very steady DC. So that's what they're up to. And again, this is the PWM. You can see the PWM that's the voltage, the black here. The red is the sine wave. That's the resultant current waveform that happens from all these pulses. There's differences in what they call carrier frequency. meaning how many pulses are they doing per waveform. Originally, they did this in like a 6-step where they had 6 pulses, and the motors really, really whined. You could hear the audible noise tremendously. Then they went to like 1,500 pulses. Now they're up as much as 5,000 to 6,000. They're not really audible. You can't hear them with a human ear, but they're going as much as 15,000, 20,000 pulses, now on very, very good inverters to get these pulses exactly what we need to give you a very good current waveform. So here's a more idea where the diodes are firing the pulses. Well, the resultant factor of that is that same understanding of technology of PWM is what's developed for radios. And so that all creates variable additional frequencies that end up happening as a resultant. So here's an idea what the PWM looks like. Here's an adjustment of what they're doing is like 30 hertz, 20 hertz, 10 hertz. They're basically just able to spread that out over, twice as much time here to allow it, because we want to create that north and south pole slower in a 4-pole machine. So that makes the motor run slower. But you really can't do that when you have a fixed waveform. The issue though is that if you look at the voltage input here, you got to watch these peak to peak voltages that come about just because of the wire, the capacitance and information that are going into the circuits. So you'll get these higher jag voltages. Well, this then creates noise back on this front power line. So what they want to do here is they'll put inductors here, or like I was showing you earlier, they'll put an inductor inside here. And that basically gives us the ability to compensate for some of that high frequency that's developed. And then you also have to be aware of another big factor in motor failure is this PWM. And if a motor is, what my rule of thumb is, if it's over 100 feet away from the output of a VFD, you really need to be cautious of what happens, because as the two wires are alongside each other, they create a capacitance effect between them, and they end up creating these higher spikes. So the voltage peak to peak can jump up as high as, here as 16, 17, 1800 volts peak to peak. Well, the original insulations in a lot of motors were much lower than that. So you put this on, after a year or two, all of a sudden you had a motor failure, along the motor lengths. And then depending on what the ripple voltages and things are, all of a sudden you get a lot of effect. Again, don't get me wrong, VFDs do have their place. They do control, and you can easily control that pump, to make it function and operate. But just be aware of this information, that you got to be watching that output peak voltage, and you got to watch the noise disturbances out on the front power line, because the power company has what they call IEEE 519 that they want to keep you within tolerance, so that this noise and frequency doesn't go feeding back to other customers. This is a little bit of a, VFDs really haven't really changed that much since the 80s, other than we have a lot of very fancy digital processors on the front. This happened to be the old original Toshiba diagram that I had back in the 80s, where everything was done by potentiometers. So we set our upper voltage, we set our acceleration or deceleration limits. We basically set all those, and that just went into the processor that drove the transistors. It had the upper voltage, lower voltage, but we had no real microprocessors at that time, so we had to do it all with the old potentiometers, read the voltage. I get this much voltage, it does this. Much harder to set up, and some of the older drives were as big as phone booths. And again, we're working to get this, PWM voltage created, so we get this ultimate current waveform. Nowadays, they've gotten much more complex. I'm not sure if they've gotten more complex for the benefit or whether it's just to make them more bells and whistles. But again, keep it back to simple operations. So one tool that I'd use a lot is this Fluke. This happens to be a 434. I think they have a 480 something now or whatever. But extremely good tool that allows us to see exactly what's happening on, because it actually scopes the waves, the outputs and inputs if you want. You can look at all your voltages line to line, which also help you tremendously. And I'm going to just play a little video. It also has a lot of macros in it that allow you to look at not only this is a harmonic spectrum here they're doing, but it also allows you to set up your flow pressures and information to get additional savings. So.
Introducing the Fluke 438 Power Quality and Motor Analyzer. The Fluke 438 is a multi-purpose test tool designed to improve troubleshooting on electric motors and minimize downtime. Whether you're in a process plant or discrete manufacturing, electric motors are critical to your operation's success. The Fluke 438 lets you quickly gauge electrical performance, power quality, and mechanical performance of industrial motors. Using three-phase electrical measurements on the input and motor rating plate data, the 438 calculates torque, the most critical mechanical performance variable, speed, load on the motor shaft, and overall efficiency, without the need to install mechanical sensors. All this with a single tool, and all while the motor is running so you don't sacrifice uptime. Power quality issues, such as unbalance in harmonics, can cause motors to run hot, eventually stressing windings and accelerating failures. Motor failures lead to costly downtime, and the cost of waste associated with inefficient motors adds up. When testing direct online motors with the new Fluke 438, you get both power quality information and mechanical performance data in the same test with a single tool. With an intuitive user interface, optimized current probes, and at-a-glance motor status screens, the Fluke 438 gives you the motor troubleshooting information you need to make better maintenance decisions and keep your plant up and running. Contact your local Fluke representative to learn more.
So what they're talking about is, especially in a VFD application, you get these harmonic spectrums that happen out there, and you get third, fifth, and seventh, and that means 3 times the 60 hertz. So it's like 120 hertz values here, 5 times and 7 times. And these are on a 3-phase circuit, which you typically see. You also get a lot of these clear out in the 47, 48. Those can clear out to the point where it's like, noises on the line. I've actually heard it where you drive down a road and you got an AM radio on, and you can literally hear the VFD creating noises out there. So that's what the power company is trying to stay away from, is to keep this noise interference. I did a lot of work in the plastic industry, and these higher frequencies also can upset other little signaling. It happens in irrigation where a lot of times you can't see it, but all of a sudden you get valve switching and other electronic circuits, failing. You got to be, aware of where this is coming from and why it's happening. And so you get all of these various harmonic amounts that come off of the original voltage waveform, and these are again 3rd, 5th, 7th harmonic. You can see these percentages, but then the meter actually counts what is that resultant amount of power. So from that, they've had to come up with all these fancy filters and informations to try to eliminate. So again, it's more coils, more capacitors that are put. This happens to be an input line or line reactors and input harmonic filters that eliminate these noises. They basically get the resultant. From that, you do get differences in in total power used. They also use these on the output of a drive. So if you have a long distance well, or like a submersible pump. I do work a lot with a company out of Italy, SARS, that does submersible motors, and they'll put a drive on a submersible motor, and it's 300, 400, 500,000 feet the ground, and they want to put on what I call a sine filter to make that sine wave back to where it is. So that's why, again, I push back to maybe keep it simple, try to put a Thyristor soft start on it, get the pump curves more accurate, and look at what that real amount of savings that you're going to actually need and utilize. And this is some of the fundamental tools back to Rob's tool. But the meter allows us to see all those blips, all that information, so we can see what's going on. This happened to be before they put the harmonic filter on and after. It also has a deviation in total power. So this was the same load. This was the before solution, read it at the 450 resultant volts here times 138 amps. And then the after was the average of 443 volts and 128 amps for the same load. So the load power is actually total kilowatts used is amps times volts and then also times power factor. But on the front of a drive, it ends up being in the 90s. So it's a little bit, don't have to worry too much about it. But so this motor was 451 volts times 138 times 1.73 for all three phases of doing it. So that was 107 kilowatts, being drawn on that. I'm sorry, 107 kilowatts. But if you take the same load without the filter, you take 443 times 128 times 1.73. That's 98. So you subtract those two. That's the difference in losses that you're losing, that you're getting charged for. So that's why sometimes your power meter doesn't always match up with what you're getting billed for, because the power company gets those resultant values in their power line where they're reading the meter, and you're not getting it there. So it's important that we keep that power clean, coming in, both the current and the voltage. Here this showed the the voltage and the current here, or here's the voltage, here's the current, and you can see it before. It had all these blips and information, but the resultant amount of power that was was up in here. So that's why the power company sees this times this, the resultant, and so that's where your power readings can be quite different, from your power company line to what you're actually getting billed for. So it's good to do a power study, look at where you're at, especially with a lot of VFD controls in your buildings, to get that as clean as possible, and do it as simple as possible, bring it back, and then look at the application. So if the pump is running off the curve, down here at let's say 70, instead of being at, let's say, a 70 or 75% efficiency sweet spot, it's sliding down here into the 60s. All of a sudden, that 15% loss is lost there. So you got 15% there. You got 6% in the VFD. The total savings, can be, roughly 21%, difference in power load. Plus, then if your harmonics are off and you're getting harmonic noise, that can also throw it off. So just don't be confused when you why things are, because almost 90% of the people out there that are using standard amp meters and voltmeters, they never see this. They don't see anything about the harmonics, don't see anything about the noise, and oh well, just put a filter on it, put a filter on the output. Yeah, but then all of a sudden you got all these extra losses. So I like to keep it simple and make the system as easy as possible. This also is a failure chart that actually has been published by ESA since clear back in the 40s. But this shows that when a motor does fail, you can actually tear it apart and see what went wrong. And it has a lot more diagrams, but this shows here. So if you have a VFD, and this shows each one of these are broken up into phases. So you have phase A, phase B, phase C, and then A, B, C. It's a 4-pole machine. This motor here saw some sort of a surge, and that the voltage in the insulation ended up being higher than what it was rated for, and so it just shorted coil to coil because all this wire has to be insulated between each other, and it got above its insulation rating, so it popped between the two and caused a failure. This you typically see here is if you have a piece of slot insulation that is burnt, that a lot of times there might have been that the bearings have failed and it started rubbing, and so it burnt part of the slot stick out that isolated it between ground. Over here on the far right, you can see this was again, voltage to ground, was caused high for some reason, and it popped and pierced the insulation on there. And then this one, the final one shows here, is phase to phase. So this, between these two pieces of slot insulation, there's a set of coils here, and between phase A and let's say this is phase B, that voltage potential is 480 here. If that voltage between phase A and phase B, got too high, it ended up wanting to jump and arc across and blew the winding out. So it gives you, resultant information. So again, I highly recommend, and we utilize in our motor divisions, we use the ESA standards, and we allow the ESA motor shops to review and analyze them. I came from that industry, and I highly believe in a really great group of people that a lot of family-owned companies have been involved in that over time. It's grown. And then one other thing here was, this is a single phase situation where the load, you can see, went all across 2 phases. One of the phases isn't even burnt, so that shows that what happened is one of the power lines got dropped and the motor continued to feed power to it, tried to compensate and keep it running, but over time it smoked the coils out. This is more information about the VFDs. I give classes on that too, but again, back to that Fluke meter, your line-to-line voltage between A, B, and C, where is it? Is it within tolerances? Is it where we want it to be? So that we ultimately, and then it also picks up, voltage spikes, and you can record over time. Again, let's recap the failure, analysis information of, well, was it originally designed right? Is it set in the right, efficiency point of the motor compared to what our voltage of our power is? So we have, under voltage, over voltage, and balance voltages. And I'll go in a little bit on cabling issues. This is output cabling of motors. And then, or did it just simply lose its cooling? Did it have a blower on it? Did it have, the fan on the motor, which wasn't bringing enough air across it? Or was it in, too hot of an environment, and the winding design, wasn't designed heavy enough? So this is a little bit on some of the metering, that's out there. You got our, voltage meters, the thru RMS, Fluke equipment. There's some other manufacturers that make this also. I'm not promoting just one brand, but this was one that I used for a number of years and found very good success. And then these are what they call a lot of hobo meters. They allow you to stick it in and read things over time. They really don't give you real accurate values, but it does give you time slots of how often and what the motor is actually truly being used over time. So when you're doing your power efficiency calculations. So that's my my main part of the discussions today. I'm going to